Okay. To continue now, we have to Professor Anna Dubova introduce to Professor Song Yongcun. You can start, Anna, please.
Okay, so let's move to the second talk. We have Professor Johnson Song. So let me just introduce you before you start. So Professor is currently a postdoc in chair for Dynamics, Control, Machine Learning, and Numerics of Alexander von Humboldt Professorship in the Department of Mathematics at Friedrichs Alexander University in Erlangen, in Germany. Before that, he received his PhD from the Department of Mathematics from the University of Hong Kong. His main research interests are numerical analysis and scientific computing in general. The topics of his research include numerical optimization, operator splitting algorithm, machine learning, and optimal control problem. He was awarded Humboldt Research Fellowship for postdoc in 2021, the EA SciAm Student Paper Award in 2022, and the Best Thesis Award in Hong Kong Mathematical Society last year. So today he will talk about physics-informed neural network for non-smooth PDE-constrained optimization problem. So please, thank you very much, and you can start.
Okay, thank you. Thank you very much. Thanks for the invitation and introduction. And today I will talk about some physics-informed neural networks for non-smooth PDE-constrained optimization problems. And first, I will introduce some background and motivation about some machine learning methods and some non-smooth PDE-constrained optimization problems. And then I will take two types of non-smooth problems, including the parabolic sparse optimal control and the elliptic interface optimal control as examples to illustrate our main ideas in the design of physics-informed neural networks on this kind of non-smooth PDE-constrained optimization problems. And finally, there are some conclusions. Okay. And it is well known that partial PDEs model various physical phenomena such as diffusion heat flow, fluid flow, elastic deformation, and etc. And for some applications, we not only need to model certain physical process, but also we need to control or optimize the considered process and to meet some certain goals. And for this purpose, a given objective functional has to be minimized, subject to a PDE or a system of PDEs, and usually with some additional constraints. And this kind of additional constraints are usually used to guarantee some realistic requirements. And then we get some PDE-constrained optimization problems. So here is a toy example. It's about to control the heat distribution of a metal bar. And mathematically, a PDE-constrained optimization problem can be written in this form. And here, U and Y are assumed to be Banach spaces, and UAD and YAD are closed convex sets. And here, G is the objective functional to be minimized. And E, Uy equals 0, is a PDE or a system of coupled PDEs. And the variable Y describes the state, for example, the temperature distribution of the considered system modeled by the state equation. And the variable U is a parameter, for example, the source term also, or some boundary or initial conditions that shall be adapted in an optimal way. And here, the constraints U belongs to UAD and Y belongs to YAD describe some physical restrictions or some realistic requirements. And this model is somehow written in an abstract form, and many very important mathematical problems can be described by this model. For example, some optimal control problems, inverse problems, and optimal design. And here we focus on some non-smooth cases. And the first type non-smoothness is we consider non-smooth objective functional. And that means the objective functional is in this form. And here, J consists of a data fidelity term and a possible smooth regularization. And that means we assume the first part of the objective functional is smooth. And the second part, RU, is employed to capture some prior information of the variable U, such as sparsity, discontinuity, and boundedness. Okay, and here we assume that R is a non-smooth functional. And to make our discussions more clear, we here focus on a specified optimal control problem. Here we consider a parabolic sparse optimal control problem, and the objective functional is given here. The first two terms are smooth, and the last two terms are non-smooth. And here, the state equation is described by a parabolic equation. And here, the L1 regularization is used to promote the sparsity of the variable U, and this indicator function is used to guarantee the boundedness of U. So here, the sparsity means that the variable U is only non-zero in a small part of the domain. In other words, U will be zero in some parts of the domain. Okay, and the second type of non-smoothness is to consider a non-smooth PDE. And here we consider interface problems. And what are interface problems? Interface problems are piecewise defined PDEs in different regions, coupled with some interface conditions. For example, the jumps in solution or flux across the interface. And as a result, the solutions are non-smooth or even discontinuous. And here is the geometry of an interface problem. Okay, here, the interface gamma divides the whole domain omega into two subdomains, omega minus and omega plus. And the PDEs are defined piecewisely in these two subdomains, and coupled with some interface conditions across the interface gamma. Again, we focus on a specific example to make our ideas clearly. Okay, and here we consider an elliptic interface optimal control problem. And here we consider a smooth objective functional. And the state equation here is an elliptic interface problem, and the solution of this PDE is non-smooth. And here, beta is a piecewise constant. That means it takes different values in different subdomains. And the interface condition is defined here. The jump discontinuity across gamma is defined in this way. That means at different sides of the interface, the solution has different values. And there's another interface gradient condition to guarantee the well-posedness of the problem. And before we moving on to the design of physics-informed neural networks for solving these two problems, we first give a brief literature review for PDE-constrained optimization problems. And first, there are a lot of work for the theoretical analysis and numerical discretization of some applications about this kind of problems. And for the numerical methods for solving this kind of non-smooth PDE-constrained optimizations. And this kind of numerical methods mainly consists of optimization algorithms plus some numerical discretization. And representative optimization algorithms include semi-smooth Newton methods, premodule active site methods, alternating direct method of multipliers, premodule methods, etc. And for the numerical discretization, and includes some finite difference methods, finite element methods, etc. And this kind of numerical methods have been successfully applied in solving different types of PDE-constrained, non-smooth PDE-constrained optimization problems. But there are still some numerical challenges. First, we note that the implementation of these methods are usually based on the so-called adjoint methodology. That means two PDEs, the state equation or its adjoint system, or a saddle point problem. And this is the first order optimality system about the PDE-constrained optimization problem are usually required to be solved repeatedly. And after we apply some numerical discretization schemes, we will have some very large scale and ill-conditioned linear systems. And the computing cost for solving the PDEs or the saddle point problems repeatedly could be extremely high in practice, especially for some high-dimensional PDEs or some PDEs in complex geometries. And another issue is these methods are strongly problem-dependent. For example, different types of PDEs entail different numerical discretization schemes. For example, for the elliptic interface problems that we considered, if we apply some...
Medina, eso amiga también, ¿eh? Sí. Ya, entonces dígale pues ahorita ya.
Okay, if we consider the interface of problem, if we apply some standard piecewise linear finite element method, it will not work very well, and we need to design some more advanced methods. For example, the immersed boundary finite element. And in addition to this kind of traditional numerical methods, recently there are some deep learning methods for solving PDEs. Okay. And some representative deep learning methods include deep race method, deep Gattke method, physics-informed neural networks, and weak adversarial networks, etc. And among these deep learning methods, physics-informed neural networks, and PINS for short, seem to be the most popular one due to its powerful in solving different kinds of PDEs, and it is easy to implement. And next, we take a very generic PDE to illustrate the main ideas of PINS. Okay, and here we consider a generic PDEs E value equals to 0, and the boundary condition is B value equals to 0 on the boundary, and here U is a known function. And the ideas of the PINS is to use neural networks to approximate the unknown function or the unknown solutions. Y here is Y. And we first construct a neural network Y height and with parameters theta. And then we specify some residual points in the domain and on the boundary. And then we use the sum of the residuals of the PDE and the boundary condition as the loss function to train the neural network. And here, Li is the residuals of the PDEs in the domain, and Lb is the residuals of the boundary conditions on the boundary. And then we put them together. Then we can train the neural network by minimizing this loss function. And after the training procedure, we will get an optimal parameter theta, and then the trained neural network Y hat x theta star gives an approximate solution for this PDE. And this is the idea of PINS for solving PDEs. And it has been shown that we can extend PINS to solve some smooth PDE-constrained optimization. And the idea is very simple. For example, we consider this a smooth PDE-constrained optimization problem modeled in this generic form. Because here U and Y are both unknowns, so we employ two neural networks to approximate U and Y. And then we just put the residuals of the PDEs and the objective functional together as a loss function to train these two neural networks. And after the training, we will get the approximate solutions Y height and U height. Okay, this is the direct applications of PINS for PDE-constrained optimization. And another idea is we can first derive the first order optimality system of the PDE-constrained optimization problem. And then we take the residuals of the optimality system as the loss function to train the neural network. And we will go back to this idea later. And the pins have a lot of disadvantages. For example, only a little or even no labeled data is required to train the neural network because we use the residuals of the PDEs as the loss function. And it is mesh-free because we do not need to discretize the domain, so it can be applied to some very complex geometries. And as we see, the implementation of pins does not depend on the formulation of the PDEs, so they can be adaptive to different types of PDEs. But when we apply pins to solve non-smooth PDE constraint optimization problems, there are still some numerical challenges. And first, for the non-smooth objective functional case, the non-smooth term will appear in the loss function. This term is non-smooth. So some commonly used neural network training technologies, for example, backpropagation and stochastic gradient methods cannot be applied directly. And for the elliptic interface optimal control problem, as we mentioned, the solution of the PDE, or here the elliptic interface problem, is non-smooth and or even discontinuous. So it cannot be well captured by the neural network, because in general, the activation functions used in a DNN are in general smooth or at least continuous. So that kind of neural networks can only capture some continuous functions, but here it is not smooth or even discontinuous. And in the following discussions, we will propose two different strategies to address these two numerical issues. And first, we discuss the parabolic sparse optimal control problems. And we first recall the parabolic sparse optimal control problem. Okay, here, the key point is this kind of non-smooth regularization terms. And to address this kind of non-smoothness, our main ideas are using operator splitting. And that means we treat the PDE constraint and the non-smooth regularization individually. And then the non-smooth problem is decoupled into two simpler subproblems. And one subproblem is a smooth PDE constraint optimization, and it can be efficiently solved by pins. And the other one is a very simple non-smooth optimization problem. And usually it has a closed form solution, or can be efficiently solved by various standard optimization algorithms or some pre-trained neural networks, for example, some CNNs. Okay, and next we will illustrate the main ideas of operator splitting. And here we consider the alternating direction method of multipliers, okay, ADMM for short. And ADMM is a representative operator splitting method introduced in 1975 for nonlinear elliptic problems. And to apply ADMM to the parabolic sparse optimal control problem, we first let YU be the solution of the state equation, and then we introduce an auxiliary variable z satisfying U equals z, and then we can reformulate the parabolic optimal control problems in this form. It is an optimization problems. It is an optimization problem with a separable structure. Okay, here we only have a very simple linear constraints, and the state equation is absorbed by YU. And as we see here, the state equation YU and U only associated with the first two smooth terms, and Z is treated separately by the auxiliary variable Z. And then to apply ADMM, we define the augmented Lagrangian functional. Okay, here lambda is a Lagrange multiplier and then beta is a penalty parameter. And then we get this ADMM iterative scheme. Okay, we first update U and then Z, and finally update the Lagrange multiplier. And we can see that when we update UK plus 1, ZK is known. That means this is only a problem associated with U and similar to Z. Okay, so ADMM is a Gauss-Seidel version of the classic augmented Lagrangian method. And for the solutions to the subproblems, we first note that this subproblem is just a simple non-smooth optimization problem about Z. Okay, and here the solution can be computed by this closed form. Okay, here S is the shrinkage operator, and it can be computed pointwisely, and PUAD is just the pointwise projection onto the admittable side. So ZK plus 1 can be very easily computed pointwisely. And for the U subproblem, it can be formulated in this form. Actually, it is just a smooth PDE-constrained optimization problem with such a modified objective functional. And its first order optimality system is in this form. Here, P is a joint variable. So as we have mentioned, to apply pins, we can use this kind of, we can consider this kind of first order optimality system. And then we use the residuals of this optimality system to be the loss function to train the neural network. Okay, so here, of course, we can, the unknown variables here is U, Y, and P. So of course, we can use different neural networks to approximate these three variables. But to reduce the training cost, we first use the first equation to eliminate the variable U, and then we get a reduced optimality system only corresponding to Y and P. And then we construct two neural networks, Y height and P height, to approximate Y and P. Then we put the residuals of the optimality system together, and we get this kind of loss function. And then we can train the neural networks Y height and P height by minimizing LOS to update the parameters. And then we can update UK plus 1 by this formula. So we can get this kind of ADMM pins to solve non-smooth PDE-constrained optimization. Okay, that is, we updated UK plus 1 by the above pins, and then the updates of ZK plus 1 and the lambda K plus 1 are computed pointwisely. And here we present a numerical experiment to validate the efficiency and accuracy of the ADMM pins. Okay, and these are the settings and the settings of the neural network and training. And these are the numerical results. Okay, we can see that the sparsity of the spatial sparsity of the control can be observed from this numerical results. And the first row is the exact control at a different time, and the second row is the computed control at different time. And from these figures, and we can see that there's no visual distinguish between the exact and the computed controls. And we can also obtain the temporal sparsity, because in our settings, we can see that if T is larger than T star, then the control variable is 0 almost everywhere in the whole domain. And the results is printed here. And we also compute the total relative error in the whole temporal spatial domain. And the error is about the order of 10 power minus 2. Okay, it is an acceptable accuracy. Okay, finally, there are some comments on the ADMM pins. Okay, it enlarges the applicable range of pins to non-smooth PDE-constrained optimization problems. And there's no need to solve PDEs repeatedly. And it is match-free, easy to implement, and scalable to different PDE-constrained optimization problems. And here, to illustrate our main idea, we only can present one numerical example and application. And more applications can be found in this paper. And in this paper, we also consider the inverse potential problem, the control of Burger's equation, and also the inverse source problem. And next, we consider how to apply pins for elliptic interface optimal control problem. Okay, we first recall that the elliptic interface optimal control problem that we consider here. Okay, and the issue comes from the interface condition, which makes the solution is non-smooth or even discontinuous. Okay. And to apply pins, of course, we here again consider its first order optimality system. Okay, this is the first order optimality system of the elliptic interface optimal control problem. And we note here, P is the joint variable, and no matter the interface conditions of the state variable Y is homogeneous or not, the interface conditions for the joint variable Y is homogeneous. Okay, here are 0. And the key issue is how to use neural network to approximate a non-smooth or discontinuous function. Right? Here, the function Y is only piecewise smooth. But we know that it can be extended to a d+1 dimensional function Y tilde. And it is smooth on the domain omega times R and satisfies this formula. That means if z equals to 1, then we restrict the high dimensional function Y tilde into the subdomain omega plus. And when z equals to -1, then we get Y is the restriction of Y tilde in the subdomain omega minus. And here, the variable Z is augmented coordinate variable that labels omega plus and omega minus. Okay, and here to illustrate the smooth extension idea, we can consider this example. For example, if we only consider these two red lines, okay, it is a discontinuous function in one dimensional space, right? But we can conduct the smooth extension. Then we get this shadow surface. It is a continuous surface in two-dimensional space. And the considered function, these two red lines are just the boundary of this domain. If we consider the variable z is -1 from in the interval 0 to 1, and z equals to -1 from in the interval 1 to 2, then we can get the original function. That means if we solve the problem in this high dimensional space, then we can recover the original solutions. And similarly, we can also extend P to a high dimensional smooth function P tilde. And since Y tilde and P tilde are smooth functions, then by the universal approximation theorems, we can apply some neural networks, even shallow neural network, to approximate these two functions. And to apply pins, we first substitute the extended function, smooth extended functions Y tilde, P tilde into the first order optimality system. Okay, and then we get this system. That means Y tilde and P tilde satisfy this system. And then we use neural networks P hat and Y hat to approximate Y tilde and P tilde. We can apply pins to solve elliptic interface optimal control problem. And the loss function is given here. And we can see that by the direct application of pins to solve that kind of optimality system, we just put all the residuals together. And here we need to, we have 8 terms. 8 terms in the loss function. That means we need to choose 8 weights to balance all the terms. And actually, in practice, how to choose these weights is very important in the to guarantee the accuracy of the solutions. And until now, there's no established rules on established rules to get us how to choose these weights. And also, we know that the boundary conditions that we marked blue and the interface conditions that we marked red are penalized in the loss function using constant penalty parameter. That means these conditions are treated as soft constraints and they cannot be satisfied exactly. And using this loss function, we have this kind of result. Okay, we can see that the errors is small. It seems acceptable, but we know that the errors are mainly accumulated around the interface and the boundary. And here the interface is a circle. So that means we penalize the boundary and the interface conditions in the loss function, bring some errors, additional errors of the final solution, okay, as indicated in this kind of the errors of the control U and the state Y. And next, we consider how to eliminate this kind of errors accumulated around the interface and boundary. And to address this issue, we consider some hard constraint strategies. Okay, that means we would like to develop a novel neural network architecture by generalizing the neural network to approximate Y and P. And to impose the boundary condition, we modified the output of the neural network. And to impose the interface condition, we modify the input of the neural network by constructing an auxiliary function for the interface. Okay. And then we explain the ideas in details. Okay, we first recall the boundary condition and the interface condition. And then we propose to approximate Y by this neural network. Okay, and here the function, the auxiliary function G, H, and phi are required to satisfy this kind of regularity conditions. And this condition looks complicated, but it just used to guarantee the boundary condition and interface condition. For example, here, function H is just the indicator function of the boundary. And G satisfy the boundary condition and the interface condition. That means we just impose all the conditions on the auxiliary function G, not instead of the neural network. And here, NY is a neural network with smooth activation functions. Okay. And then we verify whether the boundary and the interface conditions are satisfied or not. And first, we know that this H and Y is a continuous function. And then we can easily show that the interface condition of Y hat is just G0, is the exact interface condition. And the boundary condition is also satisfied by the neural network Y hat. And with this neural network Y hat, we can compute that the interface gradient condition is in this form. That means the interface gradient condition cannot be exactly satisfied by the neural network Y hat and should be penalized in the loss function of pins. Okay. And here we only present the requirements for the auxiliary functions g, h, and phi. And next, we will illustrate how to determine these auxiliary functions in practice. And we first consider the choices of g and h. And actually, if the functions g0 and h0 and the interface gamma, the boundary admit analytic forms, then it is usually easy to construct g and h with analytic expressions. For example, if omega is a unit square, then we can choose h in this form. And there are some existing works in the literature to discuss how to impose boundary conditions. And here we list some references. And the choice of phi is more delicate, and we need to discuss it case by case. And first, if the interface gamma is the zero-level set of a function that is in C2 omega, that is, it is smooth enough, then we can define phi in this way. That means in the subdomain omega minus, it is just to take the function psi x, and in the rest of domain, we take 0. And here we have an example. That is, if the interface is given by the circle, and in this case, gamma is the zero-level set of this function, and it is smooth enough, and then we can define the auxiliary function phi in this way. Okay. And this idea can be directly extended to the case where gamma is a finite union of the zero-level sets of some functions psi I and to psi n. Okay, and they are C2 omega minus. For example, if the interface is the boundary of a box, then we can put the multiplication of the level set of each boundary. Okay. And if the gamma is not smooth enough, okay, for example, here we consider that the interface gamma is only smooth enough in a small open neighborhood of neighborhood, then we can construct phi in this way. Okay. That means, okay, it looks a little bit complicated, but the main idea is, okay, the interface gamma is a zero-level set of a function phi, psi, and psi is only smooth enough in a small open neighborhood of the interface. Then we can also define the auxiliary function phi in this way. Okay, and we can check that the function phi defined in this way satisfy all the requirements. Okay, for example, if the interface is given by this star-shaped interface, okay, it is described by polar coordinates. And here, it is a zero-level set of this function, psi r theta. And it is not differentiable on the whole domain omega. And in this case, by the above result, we can define the auxiliary function phi in this way. Okay. And in the above discussions, we present some cases that we can define these auxiliary functions in closed form. And if the problem is very complicated, for example, the geometry of the interface is very complicated and it is not regular enough, then we can construct this kind of functions by training some neural networks. For example, we can train some neural networks G height and H height with smooth activation functions by minimizing these loss functions. Okay, because these auxiliary functions are very simple and they are smooth enough. So it is very easy to train some even shallow neural network to approximate them. And we separate the training, we separate the conditions, the boundary and the interface conditions from the training of the PDE. So we can also reduce the computational cost of the soft constraint pins and improve the numerical accuracy. Then with the above discussions, we approximate Y by the neural network Y height. And then similarly, we can approximate the adjoint variable P by P height, because as we mentioned, the boundary and the interface conditions for P are homogeneous. So G can be 0, and we approximate P hat. We approximate P by P hat defined in this form. And then we train the neural networks Y hat and P hat by minimizing these loss functions, because the boundary and the interface conditions are satisfied by the neural network. So in the loss function, we only need to treat 4 terms, and it is much easier to select the weights than the soft constraint pins, which has 8 terms. And here we present some numerical comparisons. And here the soft constraint pins, okay, the arrows and the hard constraint pins. And we can see that the hard constraint pins approach improves the accuracy by more than 20 times. And also, we can see that in the soft constraint pins, the arrows are mainly accumulated around the interface and the boundary. And for the hard constraint pins, this phenomenon disappears, and the arrows are much smaller than that of the soft constraint pins. Okay, finally, there are also some comments on the hard constraint pins. And first, we impose the boundary and interface conditions in the neural network architecture, and they are decoupled from the learning of the PDEs. And this hard constraint approach simplifies the training process and enhances the numerical accuracy, because we reduce the terms in the loss function to train the neural networks. And it also has the advantages of the soft constraint pins. For example, it is mesh-free, easy to implement, and scalable to different interface optimal control problems. And more numerical examples and applications can be found in this paper, including the control parabolic interface optimal control problem and some other complicated interface cases. And finally, there are some conclusions. And we first note that it is challenging to apply the pins directly to non-smooth PDE constraint optimization problems. And for the non-smooth objective functional case, combine pins with some classical operator splitting methods leads to implementable and efficient algorithms for PDE constraint optimization problems with non-smooth objective functional. And by the smooth extension, pins can be applied to solve interface optimal control problem. But it is not easy to train the neural network by balancing the 8 terms in the loss function and the arrows accumulated around the interface and the boundary. So imposing the boundary and interface conditions at hard constraints can improve the numerical accuracy and simplify the training procedures. And thank you all for your attention, and this is what I would like to share in this talk.
Okay, thank you very much for this very nice talk. So let's ask the audience if there are any questions. Juan is telling that you have your microphone open, so you can use you can use it, or also you can write your question in the chat. So please. Okay, probably while people are thinking, I have a couple of questions. So I'd like to know how do you choose the structure of your neural network? How do you choose the hyperparameters? Is it experimentally chosen, or you have some study to how to choose accurately, for example, hidden layers, or how to start your parameters? So
Oh, yeah. Actually, until now, we choose this kind of hyperparameters. For example, the depth of the neural network and the architecture of the neural network and the activation function by experience, by experimental test, because there seems no some guidelines for choosing this kind of hyperparameters. And in general, for this kind of neural networks, for example, for the interface optimal control problem, because we do a smooth extension, and the solution and the function that we would like to approximate is continuous. So we can employ some shallow neural network, and in many cases it works very well. And if the interface is complicated, for example, for the example that is a shape star interface, then maybe we need we employ a fully connected neural network with 3 hidden layers.
3 hidden layers?
Yeah.
Okay. And you have no convergence result, so it's just experimentally tried and comparing with the exact solution that you can compute by hand or other method. No, so you have no convergence results of this scheme, no?
Yeah, not yet, because in our in the current papers we focus on the design of this kind of neural networks, and we implement the algorithms to different applications. For example, different interface optimal control, parabolic interface optimal control, and even the control acts in the on the interface, different cases. And our first goal is to present the numerical results by comparing the numerical results with some exact solution or with some solution computed by traditional numerical methods.
Perfect, thank you. And do you know if there exists some convergence results for this kind of approximation, or some references paper, or do you know?
Yeah, because this kind of convergence analysis is usually conducted case by case. As I know, there's a paper studied the convergence of pins for solving some semi-linear elliptic optimal control problem, and it is a smooth case. And then the authors studied the generalization error, the convergence, and some approximation errors. But this kind of analysis strongly depends on the regularity results about the state equation. For example, in that paper, they only considered the semi-linear elliptic equation, and this kind of results cannot be extended to some other problem, for example, the parabolic equations directly. And we need to analyze this kind of theoretical results case by case.
Yes, I understand. So thank you very much. So I don't know if there are other questions from the audience. So if not, we thank you again for this very nice talk and for being with us. Okay.
Thank you.
Thank you, Anna. Thank you a lot, Professor Song Yongcun, for your amazing talk.